Hey everyone, welcome to our next video. Let me go ahead and go to our notes. So today we're going to be doing 1.3, well, this video, 1.3. And 1.3 is angular and linear velocity. This one's not too long of a section. So in general, velocity is the rate at which the location of an object is changing with respect to time. Now, if that object is in motion on a circle, we have two types of velocity. We say we have angular velocity and we have linear velocity. So let me go ahead and write that for us. If an object is in motion on a circle, we have angular and linear velocity. I'm going to give you an example of like what we're kind of talking about. So imagine for a moment, imagine that you have like a rock stuck in a tire. As you drive the car or vehicle, whatever, as the tire moves, the rock is also moving, right? So not only is that rock moving position on the circular tire, so like let's say the rock is at the top of the tire and then you move a little bit and now it's like at the bottom, and then you move a little bit and now it's at the back. So not only is the rock moving in a circular motion, that's angular velocity, that circular motion, the way the rock is moving, but then also the car itself is moving, so the rock is also moving forward. And that forward movement is what we call linear velocity. So let's go ahead and write this. So angular velocity. Also, I want to make a little kind of note about this section. A lot of this section is conversions. So although I'll give you formulas and stuff to use, a lot of it really is just converting between different units. So angular velocity is the rate at which the central angle is changing over time. And so what we mean by that is, I just want to talk about it again. Let's say we have this circle, right? The tire is on the circle, is our like circle, and I got a rock here, and then the car moves, so then the rock moves down to here, and then it moves down some more, and then it's here, and so on and so forth. So this like central angle that is changing from the angle being here, and then, oh, actually now it's here, and then now it's here, right? Oh, I didn't mean to erase, sorry. And then now it's down here. So that's what we're talking about when we're saying like the central angle changing over time. So let me go ahead and give you the unit. So this is going to be in radians per unit of time. So our unit at the end is going to be radians over a time. And so whenever we do our formula for this, we call angular velocity omega, which is this W, but it's actually a Greek letter. We call it omega. And we say that it's equal to an angle in radians, I'll say alpha, over time t. So let me go ahead and write this for you. So angular velocity is equal to the angle in radians over time. So hopefully that makes sense. We're going to have an angle in radians at the top, and then it's divided by our time. Another big conversion that we'll need to use, I'll put a little star by this, it's pretty important for this section. If you think about one revolution around a circle, we want to think about how many radians is that. And so of course I recommend you to just think about it for a second before I say it. But if I go around a circle one whole time, right, so I'm starting here and then I go around a whole time, or even if I go the opposite way, maybe I go this way. Either way, I'm going to travel the same amount of radians. So one revolution is equal to 2 pi radians. And that's because we're going around the whole circle, and a whole circle has 2 pi radians. So let's look at an example, like what these problems will actually look like. I'm going to start with just a converting time one, so convert angular velocity 240 radians per hour to radians per minute. So convert angular velocity 240 radians per hour to radians per minute. So first we start off with what we're given, so 240 radians per hour. Radians is fine, I don't want to change that, but I do want to change this hours to minutes. I'll put a 1 right here just so we have a placeholder. When I'm thinking about hours to minutes, so 1 hour is equal to 60 minutes. But when you write this as a conversion, you can either write it as 1 hour over 60 minutes, or we can see if we want 60 minutes over 1 hour. It depends on the problem, what we're looking for. If we want to cancel out hours, then we want hours to be at the top. And then also, the reason we want minutes at the bottom is because minutes is at the bottom on this unit. So since it's radians over minutes, I want minutes to stay at the bottom. Oh, I didn't mean to have the eraser on. I want minutes to stay at the bottom. Now hours cancels out. So then I'm left with 240 radians over 60 minutes. And then we can simplify. So 24 divided by 6 is going to be 4. The zeros cancel out. So this is radians per minute. So this one was just dealing with a time conversion. Let's do one where we actually have to do the angular velocity. So let's see. Example 2. I'll say a helicopter blade is rotating at 400 revolutions per minute. Find the angular velocity in radians per minute for a point on the tip of the blade. So again, we always start off with whatever they give us. So they started off by giving us 400 revolutions per minute. So that's where I'm going to start. 400 revolutions over 1 minute. And I want to find angular velocity in radians per minute. So this is what I'm trying to get to, radians per minute. So I like that I already have it per minute. That's great. But I don't want revolutions. I want radians. Well, the conversion we know for revolutions to radians is 1 revolution is equal to 2 pi radians. Now we have to decide, do we want it as 1 revolution over 2 pi radians, or do I want to use 2 pi radians over 1 revolution? Like, which conversion is going to be helpful to us? So we want to think. Since it says in radians per minute, that means we want radians at the top. And then also we need to cancel out revolutions. So we want our revolutions at the bottom so that it cancels out. So I'll multiply by 2 pi radians over 1 revolution. Now revolution cancels. And I'll just multiply across. So this will be 800 pi, and this is radians per minute. It's also possible that maybe you'll need to actually multiply out the pi, like actually do 800 times pi. A lot of the time I like to just leave them with pi, but it just depends. Alrighty, now let's talk about linear velocity. Linear velocity is the rate at which distance is changing over time. So reminding you about like the tire example, as the car moves forward, that's what makes the tire move. So the rock is also moving forward. It's not just rotating on the circle, it's also moving with the car itself. So that's linear velocity. So your formula for this is V is equal to S over T. Let me rewrite that S. Now, S is equal to alpha times R. What this really is it's the arc length formula from our last section. Really what I want you to know about this is it is so similar to the angular velocity. The only difference is that now we have to multiply by the radius. So let me put that on here, that R is the radius. So if we look at this velocity equation, if I plug in alpha times R over T, right, so not writing it as S, writing it as alpha times R, this part of it was angular velocity. So the only difference between angular and linear is that for linear, you're going to have to multiply by the radius. Everything else is actually going to be the same. It is mostly just conversions, but with linear, you have to remember to multiply by the radius. So let's do another example. This will be example 3 for us. It says a propeller with radius of 1.2 meters is rotating at 1400 revolutions per minute. What is the linear velocity in meters per second for a point on the tip of the propeller? So they kind of always set this part up like a point on the tip of something. That's just to kind of give you a reference point. Like for us, I was talking about the rock and stuff like that. That was like our reference point. So for this one, let's see. It's rotating at 1400 revolutions per minute. So that's what I'm going to start with. That's the first rate it gives me, so that's what I start with. 1400 revolutions over 1 minute. Now, just like with angular velocity, I need to get an angle out of this. So I need to convert revolutions to radians. So to do that, I multiply by 2 pi radians over 1 revolution. So at this point, I have my angle, and I am still over time, so that's great. Now I need to multiply by the radius. So for linear, you multiply by the radius. So you get your angle first, just like with angular, but now you have to multiply by radius. So my radius is 1.2 meters. So I have 1.2 meters. Now any whole number can be written over 1, so just to keep it consistent, like with fractions and stuff, I'm going to go ahead and just write it over 1 so we don't get confused. Now I need to check. So it says I want my final answer in meters per second. Okay, well, multiplying by the radius gave me meters up here, so that's great. But I need it per second. Right now I have per minute and I want seconds. So I can multiply by a conversion there. So 1 minute is 60 seconds. So I'll multiply by 1 minute over 60 seconds. And I just want to remind you, the fact that I put minutes at the top is how it cancels. And then since it's per second, I want seconds at the bottom. Now we can go ahead and simplify and just multiply across. So just to let you know, what I'm going to do in the calculator is 1400 times 2 pi times 1.2, and this is in meters, and then I'm going to divide by 60 seconds. If there's ever multiple stuff in the denominator, I recommend keeping parentheses around it, but in this case we're good. Now I rounded for this one in my notes, so I'll just go ahead and write you that answer. I got 56 meters per second. And you may notice that for linear velocity, you don't have to keep the word radians in there. That's just because we care more about the distance changing, so we actually don't need to use like the angle unit. Hopefully that makes sense. Linear velocity only cares about distance and time, so our unit is just distance over time. Okay, let's do one more. This one I'm actually going to do angular and linear, that way you can see an example with both. This is more like something I would probably ask on the test, is like I would have both in there. So this one says a 22-inch lawnmower blade rotates at 2,500 revolutions per minute. Sometimes they'll write that as just RPM. What is the angular velocity in radians per second of a point on the tip of the blade? And then I will also ask, what is the linear velocity in miles per hour? So a 22-inch lawnmower blade, I wrote blade weird over there, blade, rotates at 2,500 revolutions per minute. What is the angular velocity in radians per second? And then what is the linear velocity in miles per hour? So we're definitely going to need a few conversions. I do want to let you know that I would give you this conversion. So see how it has miles in here? We're going to need to know something for that. I'm going to let you know that 1 mile is equal to 5,280 feet. We'll use that in a second, but I would have to give you that unit. I wouldn't expect you guys to know it. Alright, so let's deal with angular first. So we start off with 2,500 revolutions over 1 minute. I want radians, so I need to get rid of revolutions. To do that, I multiply by 2 pi radians over 1 revolution. You'll notice almost all of them do that. If ever you start in revolutions, you're going to have to multiply by that conversion right there. Okay, so now we have our angle, and then I don't want minutes, I want seconds. So this is radian. Oh, keep accidentally having the eraser on. Radians per second. So I need to go from 1 minute to seconds, so this will be over 60 seconds. Now again, please let me know if you're having any questions, just send me emails or anything like that. I can also make video, like appointments with you. I'm going to do this by hand, so let's see. The zeros cancel out. Oh, minutes canceled. These two zeros cancel out. So now I have 250 times 2, which I'll write as 500 pi radians over 6 seconds. And this can simplify further because they both divide by 2. So it'd be 250 pi over 6, and this is radians per second. Now it'd be fine if you left your answer there. If you round, that's okay too. If you round, the answer I have is 261.8. Now I haven't written these notes in a little while, so if there's any kind of issues, please let me know. Okay, now let's go ahead and do the linear velocity. I'm going to start with the same thing, 2,500 revolutions over 1 minute. I still need an angle, even for linear, so because I need to get out of revolutions. So 2 pi radians over 1 revolution. And then let's see what else I need to change. I'm going to need to change my distance, most likely. And I also need to go from minutes to hours. But remember, with linear, you always have to multiply by the radius. So in our case, my radius, you got to be a little careful here. It says 22 inches, but when it's saying the 22-inch lawnmower blade, that means like it's actually the diameter. I like to be a little bit more specific on that, like on the test. But this diameter is 22 inches. So the radius would be 11 inches. So remember, I always have to multiply by the radius when doing linear velocity. So now I'm in inches over minutes. I need to get into miles per hour. So I need to go from inches, let me do this part in yellow. So I'm going to go from inches to feet. So I know that 1 foot is 12 inches. So that gets rid of inches. Now I'm in feet. And then I know that 1 mile is 5,280 feet. So now I'm out of feet. I'm in miles per minute. I want to be in miles, that's good. But I need to get into hours. So now I'm going to multiply by 1. It'd have to be, let's see, my minutes to hours, it'd be 1 hour over 60 minutes. Or do we want to use 60 minutes over 1 hour? Well, I want hours at the bottom, so I'm going to use, I hate that I keep doing this. I'm going to have to use the one with hours at the bottom. Sometimes maybe I need to just write it out. Maybe you might need to do that as well. So that's going to be 60 minutes over 1 hour. So that gets rid of my minutes. So now I'm just checking. If I look across the top, I see radians, which is good, and I see miles, which is good. At the bottom, I have hours. So this is good. I'm in the correct unit. Now it's a bunch of simplifying. I'll be honest with you, you'll have a calculator and stuff for this one. Even if you don't, remember that I mentioned that on tests, I really like to make test 1 and test 2 possible with no calculator. So I usually try to give better numbers than this for like a test question, but I like the setup of this one. I'll go ahead and reduce it for you. The final answer is 265 pi over 12. To write a little bit more work, let me do this. 2,500 times 2 pi times 11 times 60. Then you'll divide by 12 times 5,280. So this is how I would put it in the calculator. And then this is miles over hours. Now, I didn't actually multiply by pi. I left mine in like terms of pi. So I got 625 pi over 12, and this is miles per hour. So again, you can use the calculator for this one. If you rounded, it really wouldn't be a problem on the test. I'll probably put on problems, like for this one for instance, I would write on there either leave your answer in terms of pi or round to the nearest decimal, or tenths place, or something like that. So I hope that makes sense, at least for leaving your final answer. If you ever have any questions about that, please just let me know and I'll talk to you about it. But this is more like what it would look like on the test, is just having that like question that sets up to ask for angular and for linear. But just as a reminder, I would try to give better numbers on a test question. I try to make them a bit smaller and easier to work with if you don't have a calculator. So that is it for this video. I hope y'all have a wonderful day, and I will see you next time. Thank you.